Hello, welcome to this lecture on the course of computer-aided power system analysis. Till the last lecture, we have covered various methods of the load flow analysis. From this lecture and for the next couple of lectures, some lectures, we would be looking into the concept of sparsity and essentially the solution of the linear equations. So, to start with, let us look at what is meant by sparsity. So, we are looking at the concept of first sparsity of a matrix. Sparsity, when you say sparsity, it is sparsity of a matrix. Now, when we call that a matrix is sparse matrix, so sparse matrix is defined as a matrix, it is a matrix whose most of the elements are are 0. Now, the question is how this sparse matrix is really relevant to our course or to this particular course or to our discussion. So, to understand that, let us again revisit the Y bus matrix. Y bus matrix. What is Y bus matrix? It simply shows the connectivity of the entire system. So, Y bus matrix, we know that if there is n bus system, this is given as y 1 1, y 1 2, 2 2 2 2, y 1 n, then y 2 1, y 2 2 to y 2 n, and then dot 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 y n 1, y n 2 to y and n. So, these are all known, and these are of course all complex quantities that we have already seen. So, these are all complex quantities, that is fine. Now, let us recollect that what these diagonal elements are. So, diagonal elements, if we just recollect that diagonal elements y I is basically sum total of all admittances connected to bus I, that we already know, and y I j. What is y I j? Y I j is nothing but the negative of the admittance connected between bus I and bus j. So, this admittance which is connected between bus I and bus j is nothing but the line admittance connected between bus I and bus j. Now, to appreciate this, let us consider a system. I am taking just an arbitrary system, say a very arbitrary system. I am taking very arbitrary 1 2 3 4 5 6 7 8, say 9 and 10, say let us say. So, there are all 10 bus system. So, there are, let us say this is a 10 bus system. So, these are all 10 bus system. Just taking an example, it is just an example. So, all these are buses and the lines are, let us say, connected something like this. So, 1 and 2. So, this is it, and then let us say from here another one, then here another one, then here to here, then here to here, maybe here to here, maybe here to here, etc., etc. So, something like this. So, now if we look at any particular bus, any bus, for example, let us say bus 1, if we look at bus 1, so then what is happening at bus 1? So, if we look at bus 1, so there are actually 4 lines connected to it. So, this at bus 1, 4 lines are connected to it. This is between 1 and 2, 1 and 2, and then between 1 and 7, then between 1 and 9, only 3 lines are connected. So, then therefore, in the first row, so in the first row, how many? So, in the first row, the non-zero elements would be y11, y11 would be the obviously the non-zero elements, because it would be nothing but the sum total of all these admittances, this and this, and then y12 it will be nothing but the negative of this, then y17 and then y19. Now, because it is a 10 bus system, so then y bus is basically 10 cross 10. So, then therefore, this matrix has got 10 row and 10 columns, but in the first row there are only 4 non-zero elements, rest 6 are 0. Similarly, if we look at bus 2, there would be only 3 non-zero elements in that row. Similarly, for bus 3 there would be only 3 non-zero elements, for bus 4 there would be 3, for bus 5 there would be 3, bus 6 3, bus 7 would be probably 5, because 1 2 3 4 lines are connected. So, 5 and etc., etc. So, then what we are seeing is that although that it is a 10 cross 10 matrix, but then in each row not even 50% of the elements is 0, right. So, then therefore, in this matrix basically there is a so then therefore, in this matrix more than 50% elements are 0, because not every bus is connected to all the other bus. At best any particular bus is connected to only hardly maximum 3 to 4 buses. So, then therefore, in any row most of the elements are 0. So, then therefore, because more than 50% elements are 0 in this y bus matrix, so then any y bus matrix of any system is always a sparse matrix. So, we write, so we note that y bus matrix is a sparse matrix, Now, the question is, well, even if this y bus matrix is a sparse matrix, so how really does it affect us in our calculation? So, that is the question. How does it really affect us in our calculation? Or let us accept this fact that this y bus matrix is a sparse matrix, but then how does it really affect us? So, to understand that, let us look again back a Newton-Raphson NRLF polar. In fact, that same observation would be true in the case of Newton-Raphson rectangular or even for FDLF, but we are taking it NRLF polar as an example. So, in the case of NRLF polar, we have this equation J1, J2, J3, J4, and then we have got delta theta, delta V, then we have got delta P, delta Q. So, these are all known. Now, what is J1? J1 is essentially del Pi by del theta I and del Pi by del theta j, with the rider j is not equal to I. And if we look at the expression of these two, for example, if we look at this expression of del Pi by del theta j, now we have got Pi is equal to the standard Vi square into Gii plus k j is equal to 1 to n, not equal to I, Vi Vj Yij cosine of theta I minus theta j minus alpha I j. If this is the expression, so then we have seen that del p I by del theta j, the rider is j is not equal to I, would be given by V I V j y I j sin theta I minus theta j minus alpha I j. Now, now in this expression V I is non-zero because this is the bus voltage, V j is non-zero, theta I is non-zero, theta j is non-zero, right. But then y I j can be 0. Y I j is nothing but the magnitude of the I jth element of the Y bus matrix, and we have just now seen that depending upon the fact that whether any line is really connected to another bus or not, this element Y I j may be 0, may be non-zero. That is, if there is any line directly connected between bus I and bus j, this element Y I j would be non-zero. On the other hand, if there is no direct element connected between bus I and bus j, this Y I j would be 0. So, then therefore, depending upon the connectivity of this system, this Y I j can be either 0 or non-zero. If this Y I j is 0, then automatically this would be 0 irrespective of the value of V I, V j, theta I, theta j. Or in other words, the pattern of 0 and non-zero elements would be directly reflected into this matrix J1, right. If so, then therefore, if any term J I j in the Y bus matrix is 0, right, corresponding to that term, the element in this J1 matrix would also be 0. Similarly, if we also write down this expression of del p I by del theta I, we will find that depending upon the case whether Y I j would be 0 or not, that particular element would be 0, right. Similarly, if we look at the expressions of J2, J3 and J4, we will again find that depending upon the value of Y I j, that means whether there is any direct connection between bus I or bus j or not, this matrix J2, J3, J4 can have many 0 elements. So, then therefore, because matrix J1, J2, J3, J4 individually can have many 0 elements, so then overall this matrix J, this is the big matrix J, Jacobian matrix, this is the Jacobian matrix, this matrix will also have many 0 elements, or in other words, this Jacobian matrix will also be a sparse matrix. This Jacobian matrix will also be a sparse matrix. This set of equations, we know that we said that this is Jacobian, this is delta x vector and this is delta m vector. So, then this entire equation broadly can be written as j into delta x is equal to delta m vector, right. Now, what we have said earlier that delta x should be equal to j inverse, that is what we have said, that j inverse into delta m. But then we need to understand something very interesting here. We have just now understood that J matrix is a sparse matrix, right. Now, depending upon the number of bus, this J matrix can have any dimension. For example, this dimension of this J matrix, we know that this dimension of J matrix is 2n minus m minus 1 cross 2n minus m minus 1. So, this dimension we know. So, then this dimension of this matrix is 2n minus m minus 1 cross 2n minus m minus 1. So, then therefore, depending upon the value of n and m, this J matrix can be very large. For example, if n is 1000 and m is let us say just 50. So, it would be 2000 minus 51. So, 1949 cross 1949, so many elements. and if there is, let us say, roughly 4 on an average, for example, let us say if in this system roughly if there is, let us say, 4 lines are connected at each bus. So, then therefore, this Y bus matrix is roughly more than 80% sparse, because in each row, because it is an n cross n matrix. So, then therefore, in the Y bus matrix there will be in each row is 1000 row, basically 1000 column, and if any bus is connected to, let us say, at the maximum 4 on an average. So, then therefore, in each row there will be 5 in each row, 5 in each row. So, then therefore, total 5000 total non-zero elements in the non-zero elements, right. So, then the percentage non-zero elements is 5000 by 1000 into 1000 into 100. So, this is 5 and this is 200, just half percent. So, you see. So, then therefore, this is more than 99% of this matrix is 0. So, then therefore, the same thing will also be reflected here in the case of J matrix. So, then therefore, for this J matrix also more than 99% elements would be 0. So, then we have got a matrix here where more than 99% of the elements are 0, and we are trying to store all the elements first thing. So, it will be huge. So, it will require a lot of memory space, which is totally unnecessary, because for the purpose of calculation we only need to store the non-zero elements, right. I mean, 0 elements need not be stored. Secondly, even if this matrix J is highly sparse, that is, even if this matrix J has got more than 99% elements to be 0, but then when we are taking the inverse of a sparse matrix, this inverse of this J matrix is not at all sparse, it would be a full matrix. Full matrix means that almost all the elements would be non-zero. So, then therefore, we have to store this complete matrix, this particular J inverse matrix, in our memory. So, then here we have got two issues. One issue is that we have to unnecessarily store the J matrix where more than 99% elements are 0, which is not necessary. Secondly, we have to also invert this big matrix, which requires an highly computation intensive task, and to again subsequently store this completely full matrix. Now, let us understand also one very important thing. Now, at each and every iteration, this matrix J is evaluated with the current values of V I, V j, theta I and theta j. So, then therefore, after I evaluate this matrix J, so then therefore, what we have got? We have got basically the numerical values of this J matrix. So, then therefore, for this J matrix, so then J matrix will have got some numerical values which are constant values, and maybe there will be some 0 values which are constant values. So, then all these are, let us say, so then there will be some 0 values, some constant values, etc., etc. But then all these values are either 0 or sub constant values, right. So, then therefore, it is a constant matrix at any particular iteration. So, then what we are actually trying to do? So, when we are actually trying to solve this case that J into delta x is equal to delta m, what we are actually trying to do? We are trying to solve a set of linear equation. We are simply trying to solve a set of linear equation, and these linear equations are basically a set of highly sparse set of linear equations, right. Now, so far we have discussed that to solve this linear equation we have to take the inverse of this J matrix, but however, if we can exploit this sparsity of this matrices and then try to solve these linear equations, without involving this Jacobian matrix, without involving the inverse of the Jacobian matrix, then our computation burden can be reduced to a large extent. So, then and precisely that is what which is being done in each and every commercial software, that no commercial software or really undertakes the inverse of a Jacobian matrix. Rather, this set of linear equation is solved by some other method without involving this inverse of this Jacobian matrix, right. So, in the in this course, for the next couple of lectures or more, we will be looking at some method of solving a set of linear equation without involving the inverse of this Jacobian matrix, and where we can also exploit the sparsity of this equations. Now, one of the technique of solving a set of linear equations is called, very popular technique, Gaussian elimination. Gaussian elimination method. So, Gaussian elimination method. Gaussian elimination method. So, this Gaussian elimination method is actually solves a set of linear equations. Right, and it is applicable to any large set that it is. Now, let us look at how this particular Gaussian elimination method works. So, to understand that, we will look into one simple example, and essential feature of this method is that it does not require the inverse of the Jacobian matrix. Now, suppose, now to understand that, so let us take an example. Suppose I do have a set of equations, let us say A x is equal to b, where let us take that A x is a vector of unknown quantities. Let us look at x, let us take up 4 cross 4, so 4 unknown quantities. B is the vector of known quantities, say let us say this is given as B1, B2, B3, B4. So, this is the vector of known quantities, and A is a 4 cross 4 matrix, is a 4 cross 4 matrix, constant matrix. So, by the normal routine we would say that A x is equal to A inverse B, that is what we will say immediately. But then again it involves the inversion of this matrix A, and when we are talking about inversion of a matrix A, we have to calculate each and every element of this matrix. So, it is really a computationally intensive task. So, instead of that, if we apply Gaussian elimination method, we really do not have to invert the matrix A. So, let us look at that how do we do this. So, what we do is, so let us say we have A is A11, A12, A13, A14, A21, A22, A23, A24. These are the elements A31, A32, A33, A34 and A41, A42, A43, A44. So, this is the matrix A. Please note that these elements A11 to A44, these are all constant values, real values. So, we are talking about so we are basically saying that A is a real, this is a real constant matrix, real constant matrix. Real constant matrix means that where all the elements of this matrix A are real quantities, we are not talking about here imaginary quantities. So, if we expand this equation, so then what I will get? So, then we have got a set of linear equations, and those set of linear equations would be a11 x 1 plus a12 x 2 plus a13 x 3 plus a14 x 4 is equal to b 1, then a21 x 1 plus a22 x 2 plus a23 x 3 plus a24 x 4 is equal to b 2. Then we have got a31 x 1 plus a32 x 2 plus a33 x 3 plus a34 x 4, that is equal to b 3, and the last is a41 x 1 plus a42 x 2 plus a43 x 3 plus a44 x 4 is equal to b 4. So, if we expand all this this set of equation A x is equal to b, so we get this set of equations. Now, we will see that how to solve this set of equations without involving the inversion of this matrix. Now, just to let us generalize this, if let us say A is an n cross n matrix, if A is an n cross n matrix and X is an n cross 1 vector, where A is n cross n matrix, where this element are A I j, where A I j is nothing but the element corresponding to ith row and jth column. So, this is the element, we write element at ith row and jth column, and X is an n cross 1 vector is x 1, x 2, let us say x n transpose T, and let us say B is also an n cross 1 vector, which is given as B 1, B 2 to B n transpose T. This T basically stands for transpose. So, then if we have got this, so then if we expand this, what I get? I will get a11 x 1 plus a12 x 2 plus a1n x n is equal to b 1, then a21 x 1 plus a22 x 2 plus a2n x n is equal to b 2. Then if we keep on doing this, an1 x 1 plus an2 x 2 plus plus ann x n is equal to b n. So, these are the set of n simultaneous. So, we have got n simultaneous linear equations, where n can be any value. So, these are n simultaneous linear equations. So, this set of n simultaneous linear equations can also be solved by the Gaussian elimination method. So, we will first in the next lecture, we will first look at this small example, that how to solve this, and then we will simply try to generalize it for solving the set of n simultaneous linear equations. Thank you.